Hey everyone, and welcome to the 12th video on D-block chemistry, which is our final one. We've made it to the end, and in this video we'll be looking at the colour of complexes, the origins of colour, why they have their colour, how the spectrochemical series arises. So we've seen that in all the videos so far on crystal field splitting, because that determines the crystal field splitting energy, and it has its sort of basis in colour, and also the reasons for different intensities in colour as well. Let's start with the basics of colour then, why anything has its colour. So in the example I've got here, I've got this blue box called substance. Now in these videos what we've been interested in is the transition metal complexes, so some of them are blue, but this could equally just be blue paint on your bedroom wall. Like, it's exactly the same reasoning behind colour no matter what the substance is. And the reason a substance has colour is because it absorbs certain wavelengths of light. So if you take white light, which is essentially like the light all around us from the sun, say, we don't see any colour in that light. It is just light, and that's because it has all the wavelengths of the spectrum. So it has all the colours: red, orange, yellow, green, blue, indigo, violet, like a rainbow essentially. If you shine white light on a substance, that substance will absorb, or a colourful substance, can't be a white substance, that substance will absorb a certain wavelength of light, or which is corresponding to a certain colour from that white light, and the transmitted light is the colour we see with our eyes. And this is in the colour wheel, which I've got down in the bottom left here, the opposite colour to what's absorbed. So for example, we've got this blue substance here. Now that means that has absorbed red light and appears blue. It could be the opposite. If this was like a yellow substance, say, that means it will have absorbed a sort of dark blue, purplish, indigo, violet colour. There we go, and therefore appear yellow. So that's all that colour is. It's absorbing certain wavelengths of light and transmitting the opposite ones, well, the whole spectrum minus that one, but the colour is the one that's opposite in this wheel. Now, why do these coordination compounds then absorb light, or at least colourful light that gives them colours? Well, this is because this energy gap we've been seeing throughout the crystal field theory, this delta O for octahedral complexes, but also delta T for the tetrahedral complexes, it applies to both, is the energy gap is within their range of visible light. So a photon of visible light has enough energy, or the right amount of energy, more importantly, to move an electron from the ground state, so in an octahedral complex, the T2G, in tetrahedral complex, the E, into an excited state, so either the EG for octahedral or T2 for tetrahedral. And then, whatever this energy gap is, the wavelength of light corresponding to that is the colour that's absorbed, and then the opposite colour in the colour wheel is the colour of that complex, as we saw. Now, one important thing that's probably a refresher from Chemistry 1, but is really important for this next bit then, is the relationship between energy and wavelength, because the colour of light is determined by the wavelength. This gap is an energy gap, so we need to know how colour and energy are related essentially, and they're from this equation here. So we've got energy equals Planck's constant times the speed of light divided by the wavelength. Now what all this means essentially is that energy is inversely proportional to wavelength. Therefore a higher energy, like a bigger energy gap, needs lower wavelength light to excite it. Now if I get the spectrum colours again, so at the low wavelength end of things we've got blue, and then at the high wavelength, let's say we've got red. So going this way, this is increasing wavelength, and what this means is because of the inversely proportional relationship going this way, we have increasing energy. So if this energy gap is bigger, it's going to be absorbing a more blue light, and we'll see on the next slide how that changes from ligand to ligand. because we've seen throughout these videos in this latest lecture how the spectrochemical series changes the splitting energy in octahedral and tetrahedral complexes. So we saw that stronger field ligands, laser pointer, stronger field ligands give a larger crystal field splitting, and this led to things like more likely to make low spin complexes and that, but it also has an effect on the colour, as we'll see now. And the weaker field ligands, they don't have cause such a large crystal field splitting, therefore you are more likely to get a high spin complex, and again that will have an effect on the colour. So that's actually how they managed to order the ligands, was by the colour of light they absorbed. That's what's called the spectrochemical series, and that's how we could work out which split the crystal field more than others. So we've got two examples here. We'll look at chromium hexaaqua 3+ and chromium hexaamine 3+. They're right next to each other in the spectrochemical series, but we can already see from the colours that it does make a difference. So starting with a hexaaqua complex ion, that's violet. So if we look at our colour wheel, it appears violet. So that means it must absorb this yellow-green colour. So let's say it's a yellow-green. Now, if we look at the visible spectrum, where that is, that's around here, like 550 nanometers. That's where it's absorbing light because it's appearing violet. So let's put 550 nanometers. Now, looking at the chromium hexaamine 3+, that appears yellow. So that means it's absorbing light really down by the sort of blue, indigo, violet sort of bit. And therefore, that's the one shown by the black line down here. That's really like, say 420 nanometers. 420 nanometers. Now then, knowing that energy has an inversely proportional relationship to wavelength, like we saw on the last slide, we know that because the hexaamine has a lower wavelength, it has a higher energy. And that's why it's higher up in the spectrochemical series, because it causes a higher crystal field splitting and therefore absorbs light at a lower wavelength. And if it was possible with chromium, you could make complexes of all of these ligands and then see how the wavelength of light changes as we go through the series. So now we've seen why certain complexes have different colours, why some are red, some are blue, some are yellow. But there's another aspect to colour, and that's its intensity. And that is not related to the wavelength, so we can't use things like the spectrochemical series to understand that. And I've got an example here from the textbook to show what I mean by intensity. So we've got 4 compounds here. Manganese hexaaqua 2+, which is almost colourless, super pale. Cobalt hexaaqua 2+, which is pink and quite pale, but like you can still see the colour well. Cobalt tetrachloride 2-, that's a much more intense colour and blue. And then this manganese tetraoxide minus, that is a super deep colour. And intensity, as I said, isn't related to the wavelength, it's related to how much light is absorbed. And that's A here. So I've got the equation for working out how much light is absorbed here. So A, as I say, is the absorbance. And this is the product of epsilon, which is the molar absorption coefficient, which I actually won't write because it's too long, it'll take me too long. C, which is the concentration, and L, which is the path length. So essentially like how much of the solution you're looking through. Like, are you looking through just 1 centimetre of it or 10 centimetres of it? Because that obviously makes a difference as well. Now I can tell you in the photo here that the path length is exactly the same. I mean, we can see they're all the same size test tube. We're probably looking through about a centimetre of solution. In the textbook, it does say that the concentration of these complexes is the same in all 4 of them. So the only thing that can change is epsilon. And it's just this value of epsilon that's changed the intensity from so intense, so dark purple you can barely see it, to so pale that there is no colour at all. And this value of epsilon changes depending on what we call selection rules. So we've seen that the colour arises from an electron transition, so like moving from one orbital to another because of the excitation from the energy of light. But epsilon is essentially how likely this transition is to occur. And there are some rules that dictate whether it's going to occur or not. And they're here. And we'll see the effect these rules have on each of these four complexes. So before we start, just to make this a bit easier, I'm going to put what the electronic configuration and what shape each of these complexes have. So this manganese 2+ complex is D5 and octahedral. The cobalt 2+ complex is D7 and octahedral. The cobalt chloride is D7 and tetrahedral. And this manganese oxide is D0 and tetrahedral. So let's go through these selection rules. And essentially, the more selection rules that are ticked, the more likely the transition is to occur, the higher the value of epsilon, and the more absorption, and therefore the more intense the colour will be. So the first one is the Laporte selection rule, and this says that there must be a change in L. Now L is the quantum number that dictates what orbital we're in, if you remember. So L equals 0 is an s orbital, L equals 1 is a p orbital, and L equals 2 is a d orbital. So what we saw on the last slide is that when the colour where the colour arises from, for the example of an octahedral complex, is an electron being promoted from a T2g orbital to an Eg orbital. Now T2g or Eg, they're all d orbitals. So this is actually a dd transition, and by the Laporte selection rule is not allowed. So that means it's less likely to happen. That lowers this value of epsilon and therefore the intensity. I mean, you can see they're still pretty intense, so it's not like it it doesn't completely stop it happening, but it lowers it. The second rule is the parity selection rule, and this says there must be a change in symmetry label if present. So this is like the G label. So for example, in octahedral complexes, let's just do D1 because it's the easiest. We've got the T2G orbitals here, and the EG orbitals here. If we've got a D1 complex, this gets excited, absorbs some light to make it colourful. This electron will go up to here, but you can see that there hasn't been a change in symmetry label. It's gone from a T2G orbital to an EG orbital. Therefore, this one is forbidden by this selection rule, and that means it's less likely to happen and therefore less intense. For a tetrahedral complex, it's slightly different because there down the bottom we've got E and we've got T2 at the top, but there's no symmetry label, there's no G. So in this case, if we look at a D1 complex, say that gets promoted up to there, there's no symmetry label, so this is perfectly acceptable. Therefore, tetrahedral complexes are usually more intense than octahedral complexes. The final one is the spin selection rule, and that says that there mustn't be a change in electron spin. Now, this is particularly important for things like the D5 electron configuration. So if I draw that one here, we got 1, 2, 3, 4, 5. Now, if we want to promote one of these electrons, if this is going to take in some light and get excited, this has to go up here, but then it goes from an up electron, say, to a down electron. So there's been a change in spin, and this means that the spin selection rule hasn't been satisfied. This transition's less likely to happen, blah, blah, blah. You'll end up with a lower value of epsilon and a lower colour intensity. So let's apply these rules to the four complexes we've got up here, and see if we can explain why we've got this colour series of enhanced intensity. So the first one is a D5 octahedral complex. So we've seen it's D5, the spin selection rule is not satisfied, the parity selection rule is not satisfied because it's going from T2G to EG, The Laporte selection rule isn't satisfied because it's going from a d orbital to a d orbital. Nothing's satisfied. Transition's really unlikely to happen, and that's why there's very low / no intensity for that one on the left. The second one, so that's D7 octahedral. That one does satisfy the spin selection rule, so that's nice. The parity selection rule, however, it doesn't. It's still going to go from a T2G to an EG, and it's still a d orbital to a d orbital. So this one's slightly more intense than we saw. It has got colour. We can see that it's pink, but it's still not that intense, and that's because it satisfies one of the 3 selection rules. The cobalt tetrachloride, that is D7. It doesn't have this spin selection rule problem where it will flip. It can satisfy that one, so that's nice. It's tetrahedral, so it does satisfy the parity selection rule as well, because there are no symmetry labels. However, it's still a D to D transition, so we're not satisfying everything, and therefore we got 2 out of 3 right, and that's why this blue is a pretty intense colour. And then finally, we've got this manganese oxide, which, if it hasn't already, might be ringing alarm bells for you. So there is no not a change in electron spin. It satisfies that. It satisfies the parity selection rule. It's tetrahedral, so that's good. But then, what is this actual transition actually? Like, it's D0, so is it a DD transition? There's no electron to make it. So what the hell is going on here? Well, I can tell you, spoiler alert, it's not DD transition. Tick. That's why it's so intense. But what transition is actually happening if it's not a DD transition? Well, this is actually the final thing to know, and that's called charge transfer. So sometimes metals with no d electrons, D0, such as the manganese tetraoxide we've just seen, exhibit really strong colours. So like the manganese tetraoxide we saw is a really deep purple. It can't be due to a T2G to EG transition because there are no electrons to make this transition. So what it actually is called a ligand to metal charge transfer. So what happens here is we've got an example of the molecular orbitals from the textbook here. Electrons from the p orbital of the ligand will transfer into the empty d orbital, or one of the empty d orbitals, of the metal. So that's why it's called ligand to metal charge transfer. And therefore, because it's from the p orbital of a ligand to the d orbital of the metal, even that Laporte selection rule is satisfied, and that's why they've got super intense colours. So that's pretty much everything there is to know on colour and the D-block metals. Now we've got to the end of it. So here's the final batch of questions, 10 to 15 on page 1301, but don't do question 14. And I'll put the answers online soon.